Thanks for the invitation. I'm really pleased to be here with you today. It's always a pleasure to share what we are doing in space with young and motivated people, and I know that you all are motivated by space and what we might find in space also. As Hervé mentioned, I had a couple of space missions. First one was 20 years ago, second one 10 years ago, and nothing this year. So this happens often. I don't expect to fly any other mission, so I will have more time in the future to share the time I spend there for working and enjoying the spaceflight with a lot of people. My first mission was in the Mir space station. It was a short one, 3 weeks. We had it was in the 90s and 98. We had at that time French-Russian missions, bilateral missions. So it was mainly for performing French experiments in the Russian space station. Then I joined the European Space Agency. For my first mission, I was working with the CNES, which is a French space agency. And in '98, all the European astronauts have been merged. The national astronauts have been merged into a single corps of European astronauts within the European Space Agency. And so I joined ESA, the European Space Agency, in 1998. And I was assigned immediately, I've been assigned in Houston for being trained on the Space Shuttle and International Space Station. That was the first class in Houston to be trained for the International Space Station, which was just starting at that moment in 1998. And that's already 20 years ago. It's hard to imagine that. And I had actually my mission in the ISS only 10 years after, for different reasons, but in particular due to the accident of the Columbia space shuttle in 2003, which delayed the program by 3 years, at least for the non-US, non-Russian part of the station. So I flew in 1998 for a 2-month mission as a member of the International Space Station, but I went up and down with the Space Shuttle, which is not what is happening today. You probably know that the shuttle program was terminated in 2011 after the completion of the assembly of the International Space Station. So what you see here, at least all the part which is not Russian has been built thanks to the big cargo bay of the US shuttle. And if we would want today to build the same station, we couldn't do it because we don't have the space shuttle anymore. So that's important to remember that. And it took more or less 13 years to build the station. So there were some changes a little bit since 2011 when this picture was taken. But nothing really significant. It's just a reconfiguration more than adding new modules. We will see that a little bit later. So this is a presentation about how is the ISS today and what we are doing in the ISS and how is the life of the astronauts, the operations. So it's a very general one, but there will be a few details, as you will notice. And I hope I will be able to make this presentation in 1 hour, and then of course we'll have some questions and I'll be ready to answer your questions. So the crew, so that's the current crew. So as you see, there are 6 people in the station. You might see that these 3 guys up here are a little bit grayed. That's because they didn't arrive yet. So we are today in a period of rotation of the crew. So 3 crew members returned last week, actually. And so now we have just the 3 ones that you see here on the bottom. And the 3 other ones will arrive on the 23rd of March. So you can see the dates here. And they will arrive in the Soyuz. These guys arrived in the Soyuz in December 2017, and they will return in June. So you see that duration of the mission is 6 months. So that's a standard now. And these 3 ones will arrive in March, and they will stay until August. So that's also around 6 months. So that's the standard duration of the missions for the astronauts and cosmonauts today. That might change. It was not the case in the past. It might be a little bit shorter when the space shuttle was also doing the rotations of the crew. But now it's standard, because the only way to carry the people to the station is the Russian spacecraft, the Soyuz, and the life duration of the Soyuz in space is 6 months. So that's the reason why the crews are staying 6 months in the station. So as you see, it goes by group of 3, because that's what the Soyuz can do. We can only carry 3 people. So it's rotating by group of 3. So usually there are 4 Soyuz which are flying every year, 2 in spring and 2 in fall. And so that makes the rotation. So we have more or less 12 people flying every year in the station. And now we have a permanent crew of 6, but when I was on board, it was 3 only. So this crew of 6 started in 2011, I think, 2011. So you see, we have currently 3 Americans. We will have 3 Americans, 2 Russians, and 1 Japanese astronaut on board. The Japanese might be a European astronaut. It might be also a Canadian astronaut. So there is 1 seat, let's say, which is for astronauts who are not Russian or who are not American. So every other Soyuz, every 2 Soyuz, there is 1 non-Russian, non-American astronaut flying. That's the share of the owners of the station. So the big owners, of course, are NASA and the Russian Space Agency, so the Russians and the Americans. And there is 1 crew member every other mission who is not American or Russian. And in June, when these people will return, we will have a European astronaut flying, again a German astronaut, Alexander Gerst, who will replace one of the crew members. You see that the commander of the station is Russian currently, but it's rotating, so he can be American, and sometimes also non-Russian or non-American can be commander of the station. And you see also that it's 55, so 55th crew of the station. When I flew 10 years ago, it was expedition 16, so it was the 16th crew. So we had in 10 years almost 40 crews. And as I told you, since 2011, now we have 6 crew members for it's what we call expedition, which is the crew of the space station, actually. Yeah, so I think that's all I can say for the time being. You might have some questions later. This is not the end. I mean, we will have in the future 7 crew members, but we are in the phase of, let's say, reconfiguring the station for these 7 crew members, and this will happen only because we will have in the future soon, we hope, another vehicle which will carry the crew members to the station, which will be a US commercial vehicle. So actually there will be 2 ones, one which is built by Boeing and the other one which will be built by SpaceX. And this spacecraft will carry 4 people. So we will have the possibility to rotate 4 and 3 with the Soyuz, which will continue, but there will be only 1 Soyuz and 1 US commercial vehicle, which will allow us to have a crew of 7 people on board. But that's for, we hope, end of next year. Because the commercial companies which are building these new vehicles, they have to test them and they have to demonstrate, of course, that these vehicles are reliable. So that's very important, of course, for everybody. And so there will be a transition period before we are able to reach this crew of 7 crew members. This for the ISS. All right, I'm talking too much, so The housing, okay. So these pictures, as you see, this picture was taken in May 2011. Why? Because all these pictures that you see of the International Space Station, they have been taken by the crew member inside the US shuttle. So that's why we don't see really recent pictures of the ISS from outside. Because the shuttle, when it was undocking from the space station, it was doing what we call a fly around, and was taking pictures and videos to see the external state of the structure. And so all these pictures are kind of old, let's say, but they are relatively up to date because, as I told you, the station didn't change so much for a few years. So roughly, everything you see the orientation of the station here. So if you compare it to an airplane, for instance, this would be the wings, this would be the fuselage here. So these are the pressurized modules. So that's where there is life inside, actually. Everything here is not, of course, cannot be manned, and is not pressurized. So that's the main truss, the solar arrays, the radiators of the station here, and solar arrays again. And all these modules only are manned. This is a European vehicle which was called the ATV. That's a cargo vehicle that we built 5 of them, and now we don't build them anymore. So the last one flew in 2015. It was the biggest cargo for the resupply of the station, and it was built by the European Space Agency. So this picture is from 2011. I think that was the second one. Yeah, it's ATV2, so that's the second one. But we don't build that anymore. So the station is oriented more or less. I talked about an airplane. As you can see it here, that's the usual orientation of the station. This is because it's optimized for solar power. These solar arrays that you see here, they are turning to follow the sun. But this orientation of the station allows to optimize the power generation on board the station. So that's why we have most of the time this orientation. But it can be changed, actually. We are out of the atmosphere, so it can be changed. So this is it going. It's flying in this direction. Usually I have an arrow here, but I don't see it. So it's flying in this direction here. So this is the front, and this is the aft of the station. The front part, as you can see, there is the Columbus module that we delivered when I flew in 2008. We brought this module here, which is the Columbus module, European module. This is the Japanese side, which arrived a little bit after my mission in 2008 and 9. All this part here, you will see that better in the picture that I have after. This is the US part of the station. And the aft part here is the Russian side. So this module here is called the FGB. That was the first one, which was launched in 1998. That was the, let's say, the first block of the station, and the station grew around this block, which was built by the Russians, but which is owned by NASA, actually, by the Americans. And the first crew in 2000, in the year 2000, the first crew was able to live in this part of the station, which is the Russian, what we call the Russian service module, which is the main module of the Russian side. And that's the very similar to what was the core module of the Mir space station 20 years ago. It has been, of course, improved, but it's very similar to the core module of the Mir space station. Yeah. Oh, yeah. I forgot about Canada. Sorry. Canada is also one of our partners. I told you, and I talk about the crews, but they don't have a module, a dedicated module. They are building all the robotics, and this was very important when we built the station also. So there is a robotic arm here. There is a sort of robotic hand also, which can be attached to the arm and detached from the arm. So this was used, as I told you, for building the station to, you know, to grapple the modules in the cargo bay of the shuttle and attach them to the station during the assembly. But now it can be used for many things, and especially for when we have cargo vehicles arriving, we can take some external cargo and install it in the station. It can be used also to carry astronauts who are working outside the station. It can be used for changing equipment outside the station also. So this is very useful and very important for the work and for the maintenance of the International Space Station. Yeah, I told you about this picture here, which is the elements by partner. So you can see the big blue, I mean the big share is blue here. That's NASA, of course. We have the Russian side here. This module is expected for a long time. The Russians, they're supposed to bring this module, which is called the MLM, that's a scientific module. But it has been delayed several years, so now it's expected end of 2008, but we're not sure that this will happen actually in the end of this year. This is the European module, as you can see, and the Japanese side of the station, and the robotics Canadian elements here. So you can see why also, looking at these colors, we have 3 or 4 Americans, 2 Russians, and only 1 Japanese or 1 Canadian or 1 European. So this is showing also the share of the ownership of the station. So this translates into astronaut missions and also into crew time for what we call the utilization of the station, which means science and everything that's utilization. So it's mainly science, mechanic, technology, education, all these activities that the astronauts are doing. There is also a limited crew time per partner for that. That's part of the original agreements between the different partners. Okay, so a few numbers, a few features here. So you see the size of, that's an American football, but well, it's like a soccer field more or less. So it's about 100 meters in this direction, 50 meters in this direction. Used to be 20 meters of thickness. It's a little bit less now because we changed the position of one of the modules. The mass is around 420 tons. The speed, altitude first, 400 kilometers, so that's close to the Earth, not far away, but just above the atmosphere. And the velocity is about 20,200 kilometers per hour, which means 7.7 kilometers per second, which is, as you probably know, the velocity which is needed when we are at this altitude, 400 kilometers, to stay in orbit. Orbital inclination, we'll see that in a minute, 51.6 degrees. Pressurized volume, it's hard to imagine what it is exactly, but I would say a few buses, more or less, maybe 4 or 5 buses for the pressurized part, which is quite a lot for six crew members, actually. I remember that once when we were 3, I was trying to find one of my colleagues, my Russian colleagues, and I couldn't find him. I guess he was hiding for taking a nap for a few minutes. But so that's a big station. Orbital period, 91 minutes. That's the time we need to do one orbit, of course. So first thing you see, it's very close from the Earth. If you think that the radius of the Earth is about 6,400 kilometers, so that's very close, 400 kilometers. That's visible here. You see the inclination of the orbits here. I was mentioning that 51 degrees. That's the angle we have with the equator of the disk which is carrying the orbit. So more or less this disk is fixed in space, and of course the Earth is rotating beneath. So you see that each time in the next orbit, of course, we will be more west, and it takes about 15 or 16 orbits for the Earth to have a complete 24-hour rotation. What else do we see here? We don't fly over the poles, so we cannot see the poles. Even if at 400 kilometers we can see far away, about a radius that what we can see is about 2,000 kilometers. So we can see far away here, but we cannot see the poles. Okay. Actually, this disk is turning a little bit slowly to the west. So there is. This is due to the fact that the Earth is not a perfect sphere, and so that there are some tricks with the gravity. So the orbit is a little bit rotating, and as you can see, this is the Sun. The station is not flying each time directly under the Sun. I mean, the Sun can be high, it can be low, a little bit like on the Earth. So that's why also the solar arrays are not only rotating in this direction, in what we call pitch in aviation, but they're also rotating to the side, because the Sun can be also on the side a little bit. You know that you can see the station, right? As I told you, the Earth is rotating under the station, on the orbit of the station, so it's flying more and more west. So it can fly over any location which is located between plus 51 and minus 51 latitudes. Okay, so that's where we are here. We are below the 51, so we can see the station. The conditions to see it has to be, the station itself has to be in the sunlight, and we have to be in the obscurity, more or less. So that means we can see it only in the morning or in the evening. Okay, and of course, the station has to fly above us. That's one condition. And of course, the sky has to be clear. That's an important thing. That's the same when we are on board. If we want to take picture, we need clear skies also for to make pictures of the ground. So here it tells you when I'm trying to find. So in order to see it, the station doesn't emit any light. Okay, so if we want to see it, it has to be in the sunlight itself. And it's very bright, actually. I don't know if some of you saw it before, but it's very bright. And you can see it crossing the sky in a few minutes. So for this region here, I know that some of you are coming from other parts of the world. Okay, so the launch, as I told you, today it's only with a Russian vehicle, the Soyuz. So we have to go to Kazakhstan for the launch. And that happens 4 times during the year. So that was a launch of Thomas Pesquet, who is the last French astronaut to fly who flew in the International Space Station. He launched in November 2016, and he returned in June of last year. And it was a night launch. It can be night, day, winter, summer, anytime, of course. And this launcher is very old, but it has been, of course, upgraded. But that's more or less the same launcher which was used for the first man to fly in space, Yuri Gagarin, in 1961. But it has been improved again. But it's a very reliable launcher, and it's called the Soyuz also. In Russian, Soyuz means Union, and the spacecraft also is called Soyuz, and it carries 3 people. So, what is the objective? You see the launcher is oriented, of course, vertically, so we're going to fly first vertically. So what's the purpose of flying vertically? Because we want to be in orbit with a horizontal speed, right? So do you have an idea why we have to launch vertically first? Escape the atmosphere. There is, of course, an atmospheric drag, which is, of course, acting on the vehicle, so we want to go as fast as possible out of the atmosphere, and the best way to do it is to fly vertically. But you will notice that it started already to rotate, to finish with a horizontal orientation, and Actually, during 2 minutes, we will fly with a relatively vertical attitude, and then it will go more and more horizontal, and we'll finish only with a pure horizontal inclination to be able to accelerate in the direction of the orbit. So the launch itself, between the T0 of the launch and when you reach orbit, it's about 8 minutes and 50 seconds. So it's very quick, but takes time, especially for a video. So we actually have 3 people. So here we are about 2 minutes into the flight, and you see the launcher is still in a relatively vertical attitude. That was the first stage separation. You saw the 4 boosters being separated. And we'll continue to climb, but we will be more and more horizontal, as I told you. So here you can see we are about now 3 minutes. So it's about 45 degrees orientation, attitude. We are in the second stage. So now we are that's the end of the second stage. It's about 300 seconds or 5 minutes, 300 seconds, yeah. So we are 2/3 almost into the flight. So you see we are now on the 3rd stage. The second stage has been separated, and you probably saw also that the fairing, the protection around the Soyuz, the crew vehicle, which is here, has been jettisoned because we are out of the atmosphere, and we're almost horizontal now. So I will show you how we arrive in orbit. You will see that it's interesting because the engine will stop, of course, and then it's like, hitting a wall almost. So you're going from 3 Gs to 0 Gs in less than a second. So you will probably see that here with looking at the dog, by the way. You see the crew is very quiet. There is nothing really to do during the launch. It was quite rough. Anyway, that's the way you reach the orbit, and then you have to fly and do what we call the rendezvous and docking with the station. So that's the vehicle when it's separated from the launcher. So there are 3 parts in this vehicle. 3 parts in the vehicle. This is the part that we saw just before, where the crew The central part here is where the crew is during the launch and for the return. So that's the most protected one. This one is protected also for the re-entry of the vehicle. When we come back, we need to protect because of the high temperatures which are involved when you are doing the atmospheric re-entry. So this part is really the safe part of the vehicle. The front part here is used only in orbit. That's called the orbital module. So that gives the crew more space when you are on orbit. And it's also where you have some equipment like the docking probe here, which is used for catching the station and attaching, the initial attachment to the station. And the aft part is not pressurized here, so you cannot get inside it. And it's for the engines, tanks, propellants, and for the solar arrays and all these kind of things. And these 3 parts are separated when you return to Earth. They are separated, and these 2 ones are the orbital module and the service module are burning in the atmosphere, and the central part is protected and returning the crew, and then you will see that later, landing under a parachute. So usually it takes 2 days, well, in the past, it took 2 days to do the rendezvous, the station, and dock. So that's quite a long time in a small vehicle, you can see. But the Russians managed to improve that, and for a few years now, they are able to join the station in 4 orbits, so that's about 6 hours between the launch and the docking, which is, of course, very good for the crew, but that makes also a very long day, because the day of the launch started very early, so you have to get into the vehicle, and I mean to prepare several hours before the launch, and you have to get inside the vehicle, and then you have to do the launch, the rendezvous, the docking, and then you have a few things to do when you arrive in the station, so that makes a very long day. Having 2 days, it was not too bad, I think, but except the fact that you were in a very confined module during 48 hours. So that was the docking of Thomas Pesquet and his crew in November 2016. So he had a 2-day, 48 hours rendezvous, and this is the final phase. So the final speed for the docking, I mean the relative speed between the vehicle and the station, it's a few centimeters per second, around 35 centimeters per second. So that's very slow, of course, in terms of relative speed, relative velocity. You can see that here. And there are 4 docking ports on the Russian side of the station, where you can have usually 2 Soyuz, 2 crew vehicles docked, and 2 cargo vehicles docked. So that's usually what we have docked to the station. So each time you have, for 6 crew members, you will need to have 2 Soyuz docked to the station, of course, because that's also the lifeboat of the station. If there is any problem with the station, you want to escape, you want to do an emergency return, you need to have your vehicle, of course. So that's why we have 2 Soyuz when there are 6 people on board. And as of now, before we just have 3, we just have 1 Soyuz, obviously. And this is the final approach and docking. You see, it's very slow.
So it's fully manual process.
Well, it's in principle it's automatic, but it can be manual. If there is something wrong, the commander can take over and fly it manually.
So the thrusters fire automatically.
Excuse me?
So the thrusters fire automatically.
Yes, yeah. In principle, it's automatic, but it happens regularly that the commander takes over, and the crew is trained for that, of course. Okay. Usually, when you arrive, you have what we call PAO, so that's a public event. That's not so much public. It's mainly a video conference with the ground and with the Moscow Control Center, and the crew is talking to the officials, of course, and also to their family. So that's just after the arrival of the Soyuz in general. So that's a nice moment. But that was a very long day, so they are probably very tired at that moment also. And this is one of the docking ports that you can see here on the Russian side. So this vehicle was docked underneath the station, for instance. That's the usual place for 1 Soyuz, the other one being on top here, on the top side of the Russian side of the station. There is another docking port here. And what you see here is a Russian cargo. That's another docking port, and there is another one on the aft here, which can also be used by a Russian cargo and was used also by the ISA cargo, the ATV in the past. So working, I try probably to be a little faster. As I told you, that's a 6 months mission, just to show you the scheme. This is the duration of, that was for our French astronauts, so that the 3 crew members, they going up with the Soyuz, so that starts here. Soyuz is lasting 6 months in space, so that's the duration of their mission. And so you see the other Soyuz is on top here. So you see that this one is leaving earlier, and there is another one arriving, and which all these Soyuzes are again staying 6 months attached to the station, so the crew is staying 6 months attached to the station. Here you have all the docking ports. So these are the Russian ones on the top here, and you have the American docking ports on the bottom here. So you see they're not all on the American side. Currently, it's not all filled with vehicles, but it will be the case again in the future. So I will show you the US vehicles later, but there are also 4 docking ports, just to let you know, on the US side. And the mission's standard duration is 6 months again. So this is what the crew see every morning on its plate for the day. Okay, so that's the plan, the work plan of the day, let's say. So that's on the computer, of course. You have the 6 crew members here. You have all the activities that they have to do. What you see here in what they call DPC, it's a daily conference. So in the morning and in the evening, there is a conference with the ground control centers, with all of them, which is lasting about 15 minutes. So this starts usually around 8. First, I forgot to tell you, but the station is working in GMT. So that's more or less the UK time. Or the English time. So that's very convenient when you're working on the ground in Europe, because you will have to work with the station in your normal working hours. You don't have to sleep shift, as it is the case in the US or in Japan, for instance, and even in Russia a little bit somehow. So what the times that you see here, that's GMT. That's the standard station working time. And all the blocks here are the activities for each crew member. So if you click on this, you will have a lot of information coming with all your procedures, what you have to do, your procedures, the stowage, what we call the stowage locations. So that's where all the tools and equipment that you need are for this activity and so on. So you have plenty of detail when you click on this. But that's actually what the crew sees every morning. And what you have here on the top, that's the communication with the station, between the ground and the station. There is a network of satellites, communication satellites, which are in geosynchronous orbit, and which are relaying the communications and data and commands also for the different control centers around the world. We have a control center in Houston for the station systems and US systems, of course. We have one in Huntsville, Alabama for US payloads. We have one in Europe, in Munich for the Columbus module and the European experiments. We have one in Moscow for the Russian part of the station, and one in Japan, near Tokyo. It's called Tsukuba, for the Japanese activities, obviously. And you see that we have communications almost continuously during the day. See here, there are sometimes some breaks in communication, but not too much, which was not the case at all with the Mir space station 20 years ago. We had communications maybe 10, 20 minutes per day sometimes, so it was not, we didn't talk too much to the ground. Logistics, I will show you all the cargo vehicles. So this is a Russian cargo vehicle, which is called the Progress. It's very similar, you might have noticed, to the crew vehicle, but it's a cargo vehicle only. And I think that's the one which is the most used. I think we are reaching now the 70th Progress vehicles launched by the Russians since the beginning of the program. So that's a very important one, of course. This is a Japanese vehicle. And you can see that the Japanese vehicle is, on the Russian side, the vehicles, like the Soyuz, are docking automatically. That's not the case on the US side. The Japanese vehicle is docking on the US side of the station, but it's just coming and flying near the station, and then it's grappled by the robotic arm of the station. So the crew is grappling the vehicle and then install it to the station. So that's the robotic arm that you can see here, and it has been catched or grappled here. And and then it will be installed like a normal module on the US side of the station. So it's called HTV for the Japanese vehicle, Kunotori, which is a bird, I think. I'm not sure which one, but that's a bird. That's the name of the vehicle. And the seventh one is expected now. So this is one I was talking in the beginning of my presentation about the US commercial vehicles. I talked about the crew vehicles, crew commercial vehicles. That's the future. But we have now a set of two US commercial cargo vehicles. One is launched and built and launched by SpaceX. It's called the Dragon. We had, I think now we will have the 14th one arriving. This started in 2012, I think, but we're expecting the 14th one already. Particularity of this Dragon vehicle, you see the shape here. It looks like the, I don't know if you remember the Apollo capsules. So this is the shape which is clearly will return to Earth. Okay, so that's the only cargo vehicle which is allowing to bring some equipment or experiments or whatever back to Earth. Of course, in a good state. The other vehicles, they are just burning into the atmosphere when they return. So they are used mainly for the trash. So they are, once they have delivered the cargo, and all the cargo has been transferred, the crew will transfer all the trash in these vehicles, and all this will burn in the atmosphere. And so that's where we are getting rid of all the station trash. But this vehicle, the SpaceX Dragon, is able to bring some cargo back. This is another vehicle which is called Cygnus. That's the company is Orbital 80K. You see so this one is not bringing back anything. So it's really, if you look at it, it's really like a module of the station. So it's used only to deliver the logistics and to bring back the trash. And this will also be grappled by the robotic arm of the station, and will be attached to the station like a normal module on the US side. When a vehicle arrives, you see there is a lot of cargo. This is Thomas Pesquet and Peggy Whitson. They have just opened the hatch of one of these vehicles. I think that's a Dragon here, SpaceX 10. Yes, it's Dragon. And you see it's filled up to almost to the hatch here. So there are a lot of things to transfer when these vehicles arrive, of course. And there are also some external cargo on the other side of this Dragon vehicle, which is used for installing with a robotic arm external equipment outside the station. So you see they're wearing goggles and masks because we are never sure when we open the hatch there will be no debris floating. It's usually clean before the launch, but you never know. So might be some pieces of metal or small dust of metal which is flying in weightlessness, of course. So that's why they're wearing these masks and goggles. But when we are sure it's clean, then we can get rid of the mask and goggles. So science, this was a program for just ESA, the European Space Agency, and CNES, which is a French space agency, for the mission of Thomas Pesquet, who is our French astronaut who flew in the station. So that was just a program for the European Space Agency and the French Space Agency. So you can imagine that there is the same number, or at least, and more than that even, for the other partners, and especially for the US. Also, they have a long list of payloads. I think that overall, for each what we call increment, so a mission duration of an astronaut, there are around 200 experiments to perform during the mission. So that's of course a lot, and that's today really the important part of the work of the astronauts on board. And that's what actually the station was made for, to perform science and technology experiments and so on. So this is just to give you a flavor. Okay, so there are a lot of details here. I will not stay a long time on this, but you have, what is important is the different disciplines of science which are tackled during our science activities in the station: biology, biotechnology, earth and space science, educational and cultural activities, human research, of course, physical science, technology development and demonstration. So the station is not only dedicated to fundamental science, but also to prepare for the future. So we are also developing the technologies, the new operations, etc., which will be used when we go further and we continue to explore the space with. I'm talking about human exploration, of course. So I will not go too much into the details, but as I told you, for instance, for now, expedition 55 and 56, you see we have 184 experiments, so that's almost 200. And since the beginning of the station, I think, I don't see the number here, but I think now it's about 2,400 experiments which have been completed. This is the Air Force. So this is a scientific work here. For instance, this is an instrument which was used to measure muscle atrophy. You know that we are working in weightlessness. So there are a lot of these. Weightlessness is fun, but it's not the friend of the human being, actually. And it creates a lot of problem, in particular on muscles, bones, and other things. And so this experiment was dedicated to measure the atrophy of muscle during a 6-month mission. So this has been done recently during the Thomas Pesquet's mission. So that was in 2017, last year. And here it's helped by a Russian crew member. So you see that's inside the Columbus module, the European module. So you see how it's crowded here. A lot of equipment, cables, everything has been deployed, and you can imagine everything has to be restored after that. So that's a lot of work, actually. So this is another experiment which is called Fluidics, which was a French Space Agency experiment. In that case, the behavior of fluids in weightlessness is something very important, of course, not only for fundamental science, but also for the space operations, for the satellites, for the vehicles, of course, because we have a lot of fluids, and if we want to optimize the behavior of fluids, we have to study how they behave in weightlessness. And there is a lot of progress which is done continuously in that area for years and years now. That's another experiment. That's a NASA one, this one, which is which has to do with education also. The idea is to fly spheres. That's the name of the experiment. To fly spheres in in close together, and the software. This is an experiment which has been taking place for several years now, and the software is actually developed by students. It can be changed, so there are challenges which are organized between the different schools and students, and so that's an interesting experiment which has been there for quite a long time now, and that's more in the area of education, which is also something that which is very important in the astronaut activities on board. This is another. Here we are in the area of technology demonstration. You can see this module here. It's an inflatable module, so it has been launched, attached to the. So this is on the US side here, but looking aft, and then it has been inflated, and it's allowing to study this kind of technology for the future. Inflatable habitats. This is something that might be important for the future, and it was originally mainly dedicated to study the atmosphere inside the module, because of course you can imagine an inflatable module that's a very special material, and they are off-gassing, so These kind of problems, of course, in the future might be important to know if we can use inflatable modules and have a non-toxic atmosphere inside the module, and these kind of objectives for these technology experiments. Now it's used, I think it was designed to stay 2 years for this technology demonstration, and now it's used as a storage module. It's very important storage on board. I talked about that a little bit later, but it's now a storage module. Spacewalks, this is also something which is happening from time to time, regularly, I would say. This is Thomas, of course, who went outside. He was, I don't know if I should have a video here somewhere, but let's see. Hello. Okay, so the video is here now. So that was his first spacewalk, and they are regularly, I mean, spacewalks in the station, might be on the Russian side, might be on the US side, but there are usually maybe 10 what we call EVA, extravehicular activities, every year. It might be for maintenance of the station, it might be for installing experiments outside the station or for repairing something. Sometimes it might be for contingency reasons, because something is breaking outside the station and the crew has to go out and change something. And in that case, that was an upgrade of the station batteries. And Thomas Pesquet was part of this, this EVA. That's another one that he did in March 2017. He's lubricating the some of the mechanism of the robotic arm of the station. So that's also maintenance activities. Here he was testing, there was some problem of leaks in the thermal loop, outside thermal loop of the station, and he was trying to find if there was a leak somewhere. So this was spotted by the ground controllers, but it has to use the astronaut to check, to do what we call troubleshooting, to see if there were some leaks in some part of the external thermal control system of the station. Robotics, I mentioned that before. That's a nice picture because it shows you all the robotics elements of the station. You have the robotic arm here, which is existing from the beginning, almost from the first 4 or 5 years of the station. This is the robotic hand I was mentioning also, and this can be disconnected here at least. No, yeah, here. The robotic hand is used to do some finer tasks, you know, like screwing, unscrewing, or drilling sometimes, or doing this kind of thing that you cannot do with the main arm, which is more used for, you know, grappling big modules than for doing fine tasks. You see the arm here is based what we call the MBS, Mobile Base System. So there is a rail track on the forward truss of the station, and there is a sort of wagon, if you want, on this track, and it can move. And the arm itself can be attached to this wagon and can move, and if it's moving, it can reach things which are further on the left, on the right of the truss or whatever. Yeah. Another important feature about the arm, it can walk the station. So you see that so the arm is starting here. So you see that what we call the end effector, so that's the tip of the arm. And there is another end effector here, which is exactly the same, okay? And throughout the station you have what we call grapple fixtures, so you can grapple with these end effectors, with these tips of the arm. So for instance, in that case, the arm is connected to the station here, but if you can imagine that it would grapple another fixture here, and then it would disconnect from here, so then it's able to walk from one part of the station to the other part like this. So that's also one of the big flexibilities of this robotic arm. It can walk and it can be based on a wagon here on a rail track, and so it can move actually and do things in various parts of the station. So that's very smart and very reliable also. So here you can see almost everything of the robotics system of the station, which is again developed by the Canadians. So that's a robotic station here inside the station in the what we call the cupola, which is a very nice viewpoint for the station. It's underneath the station, and you see that there are some windows. So that's unfortunately it was not there when I flew, and it arrived a few years after. And but that's a very nice place to be, definitely. And you see all the elements of the robotics workstation here with the joysticks and controllers. And one of the tasks of the crew now, maybe I should mention that in the beginning, all the robotic tasks were performed by the crew members only. But it's time consuming. And now, for a few years now, the ground controllers are able to control the arm. And the crew is doing less and less robotics tasks. So the ones which are remaining for the crew is grappling this vehicle, because you can imagine that when the ground controllers are controlling the arm, there are some delays because all these commands and telemetry takes time. It takes 2-3 seconds to arrive or to reach the station. So if the vehicle is moving a little bit, you cannot do that from the ground. So far the crew is the crew only is grappling the cargo vehicles, and the ground is doing all the other tasks which are only working with station equipment outside the station. Okay, as I told you, weightlessness is not a friend for the human being. So there are a lot of medical exams which are done. I saw you before an instrument for measuring muscle atrophy. There was a problem which was discovered a few years ago in the station. It's what we call the VIIP, not VIP, but VIIP, visual impairment and intracranial pressure. So what it is, actually, it's degradation of the vision of the astronauts due to some side effects of the weightlessness, and mainly to the increase of the pressure inside the crane. So this is not something which is monitored very carefully during the whole mission. But there are also other exams that we have to do during the mission, because, as you can imagine, we want to check regularly the health of the astronaut on board, because that's very important, not only for the program but also for them. You can figure out that, I guess. So this instrument is used for measuring, I guess that's for measuring the pressure of the eye, actually. But there are we have ultrasound also for monitoring the eyes. This is very important. Health maintenance, if you don't do anything during 6 months, no exercise inside the station, so you will be like someone who spent 6 months on a bed in a hospital. So that's of course very bad for your body, and so every day there are almost 2 hours of exercise to be done by the astronauts. And this is one of the instruments which is used for. This one is for muscles training. And we have 2 other ones, one for cardio training, which is a sort of bike, and there is another one which is a treadmill, actually. And these 2 instruments are the basis of all the health maintenance for the astronauts and cosmonauts on board. Maintenance of the station itself, this is also, of course, very important. When Thomas Pesquet, our French astronaut, arrived on board on the first week, the toilets failed on the US side, and hopefully there is another toilet on the Russian side. But you can imagine when you have 6 people for just one toilet, that's not very good, of course. And during this first week of his mission, we were really feeling the motivation of the crew to repair this US toilet very quickly to be able to recover the second set of toilets for the crew. That's very important. But that's just one example, of course. But you can imagine the same thing for other things like carbon dioxide removal or this kind of, or water production, or everything has to work, of course, well, and to be reliable enough so that you don't spend all your days by repairing these things. Of course, that's very important. But we're also progressing in this area. So this was, by the way, maintenance of the carbon dioxide removal system of the station. That's Jeff Williams. That's a picture from 2015 or 14, I think. And that's a big rack that you see here, which has been tilted, and Jeff is working on it. Education, I told you, that's also something which is very important. The astronauts are spending a lot of time to perform some education experiments. So that means experiments which are created and developed by schools and students, and this is happening regularly. And there are also a lot of in-flight, what we call in-flight calls, or the astronauts will talk to students, or to the public, or to. So there is a lot of activities in the station which are done for this return to the education, let's say, to motivate the young people for math and physics and science and all these kind of things. So, so Thomas here is recording a video message for UNICEF. So that's one part of these activities. But he spent a lot of time doing that. That's part of the normal work. But he also spent a lot of time doing all the social media stuff, which is actually not really part of the daily work. So he had to do that in the evening. And when he came back, he told us that that was also very time consuming. So this is something new, because in the past we didn't have these social media tools on board. So now the crew has an internet connection and is able to do all these things, but there's also additional work, of course, for the crew members. Public relation, I told you, this was with the Academy of Science in Paris. So that was one of the things that Thomas did during his mission. And the last, I think that's the last slide. The idea was to play an organ in Montreal, in Canada, from on board the station using an iPad. So it was, let's say, an attempt to do it. There were some technical issues, but so just to show you one of the things we are asking the astronauts to do from time to time. So there was a lot of people in this opera in Montreal. Okay, I think I will show you the return. So I'll, because I don't have time anymore, but I want to leave time for your questions. But I will show you how the crew is inside the Soyuz for the return. So that's the arrival. When you are touching, well, it's more than that probably, but it's very, very short, on a very short time. But I don't have time to show you everything, but as you see, the final part, there is just the central part of the Soyuz which is remaining. The other parts have been separated and burned in the atmosphere. So the parachute is opening a few kilometers above the ground, and then when you arrive at about 1 meter from the ground, there are some retro rockets that will fire. You will see that here, underneath here. And this is for just slowing down the vehicle just before you hit the ground. So the video from inside the module that I showed you before, don't be afraid if you see a lot of fire and smoke here. That's normal landing. So that was just to slow down the vehicle, so that makes the arrival a little bit less rough, let's say, for the crew, harsh for the crew. So we will see the same thing from inside. So you see that's the retro rockets firing. Then you have the second, let's say, vibration, which is hitting the ground. And usually the module is still, rotating a little bit. So we saw very briefly a third motion of the vehicle. at the end. So you see 1, 2, and it's still moving, and then it stopped now. Okay. So you see how the arrival is inside the Soyuz. And that's, of course, the nice part, because then you have to go out of the vehicle, and usually it's not very easy. When you spend 6 months in weightlessness, all of a sudden being out and try to start to walk and to do normal things of life is not that easy, and you're usually feeling some motion sickness. And usually after you come back, there is several weeks of what we call rehabilitation, so that's based on physical exercise, and just to be able to come back slowly in the same state that you were before you launch. Okay? All right. Sorry, I've been a bit longer than I expected, but I'm ready to take any question, and I have no time limitation. Hervé, let me know, of course, and that's of course depend on your time also. But I'm ready to take questions. You like these pictures? Thank you.